New method could pave the way to creating the heaviest element. Scientists have demonstrated a new way to produce super heavy elements. Using this method, they managed to produce livermorium, the third heaviest element with atomic number 116. This achievement paves the way for the synthesis of element with atomic number 120. If successful, it would be the heaviest element in the periodic table. The Lawrence Berkeley National Laboratory, LBNL, in the US has managed to produce livermorium, the third heaviest element with atomic number 116, in a way that could be used to create element with atomic number 120. Livermorium was first produced in 2000 by scientists from the Joint Institute for Nuclear Research in Dubna, Russia, in collaboration with researchers from LBNL. The third heaviest element known in nature was created by smashing a beam of calcium-48 atoms against a target made of curium. In the new study, LBNL scientists used a beam of titanium-50 atoms and a plutonium target to create livermorium. The Berkeley team presented the results of the study at the Nuclear Structure 2024 conference in Lamont, USA. The description and results of the work have also been submitted for publication in Physical Review Letters. They are currently available on the AR14 preprint database. LBNL has discovered 16 of the 118 elements so far, and there is a good chance that the next one will be discovered, the heaviest of them all. Super heavy elements are those that have a large number of protons in their nucleus. This number is designated by the letter Z and is the so-called atomic number. A few years ago, the periodic table was supplemented with 4 new elements. The heaviest of the new elements and the heaviest element in the periodic table, called oganesson, has Z equals 118. It was named after the academician and discoverer Yuri Oganessian. It was first obtained in 2002 by bombarding californium-249 with calcium-48 atoms. Super heavy elements are very important from a scientific point of view. They test the limits of nuclear theory, showing how many protons and neutrons can coexist in an atomic nucleus before it decays. And because the electrons in the inner shells of these atoms are so strongly attracted to the abundance of protons with the opposite charge, they spin at nearly the speed of light, distorting the shape of the nucleus. The synthesis of super heavy elements is simple, or at least it looks that way. Scientists fire beams of ions of a lighter element at a thin target made of a heavier element in hope that the 2 nuclei will combine. The sum of the protons in the beam and the target must be equal to the number of protons in the atom you want to obtain. All the targets, projectiles, and bombardment energies must be carefully selected. The probability of the expected nuclear reaction occurring, culminating in the creation of a nucleus with a new composition for a fraction of a second, is very small. Super heavy elements are defined as those with a Z above 104. Those with atomic numbers between 105 and 118 have been produced experimentally, but are unstable and have very short half-lives, so they are of academic and research interest only. The latest super heavy elements with atomic numbers between 114 and 118 were discovered using a calcium-48 beam, whose number of protons and neutrons makes it stable and more likely to combine with target nuclei. However, this approach ended with oganesson, which has an atomic number of 118. Because the heaviest targets that ion beams hit can be created from californium-249, which has 98 protons. Fermium, which is more massive than this, with 100 protons decays too quickly to be used. Therefore, physicists started using heavier but less stable elements. It turns out that to produce element 120, you need a beam with 22 protons, not calcium 48, which has 20 protons, but titanium 50. Germany's Helmholtz Center for Heavy Ion Research, GSI, was the first to search for element 120 using a titanium beam that fired 4 trillion ions per second. However, scientists estimated that the experiment would have to last at least a year before a single atom of 120 could be created. The search that began yielded no results. GSI has since suspended its efforts while it remodels its lab. The LBNL labs are home to the 88-inch cyclotron. In this accelerator, scientists generate more powerful beams that fire about 6 trillion ions per second. First, scientists heated titanium-50 to a temperature of 1800 degrees Celsius, at which it began to vaporize. Microwaves were used to knock out 12 of the 22 electrons. The prepared titanium was then fed into the accelerator and accelerated to about 11% of the speed of light. It was then bombarded against a plutonium disk that was spinning 30 times a second to dissipate the heat of the collisions. Most of the ions passed through the target intact. However, in rare cases, a direct hit combines titanium and plutonium. In recent experiments using a titanium-50 beam and a plutonium target, detectors at LBNL twice detected livermorium-116 atoms, which decayed into flerovium-114 and then copernicium-112 within milliseconds. 2 livermorium atoms were obtained in 22 days of accelerator operation, much less time than the researchers expected, which they say indicates that titanium and plutonium combine more easily. Scientists estimate that it will take at least several years from the start of the work to produce element 120, if it is successful at all. A plutonium target was used to produce livermorium, but a californium target will be needed to synthesize element 120.